All right, so announcements. First off, I don't know if you saw the post, but slipped into the spec and also posted on Ed that if you want to use a large language model like ChatGPT or Copilot or whatever, for phase 2 of project 3, you may go arbitrarily hog wild. Just make sure to cite your sources. And I gave some tips about how it might be useful. I don't know if large language models in the current moment are actually that useful for phase 2, but maybe they are. So if you want to try, go for it. Secondly, at some point, by the way, I'm going to try and in my reflections on this project later, I'm going to find what people did. And then if you found really cool ideas, I will incorporate them into 61B next semester. So I think these tools are really, really useful. So may as well start bringing it in. Second, my office hours, they're totally normal. They're in 779 Soda. See you at 2 if you want to come. Right. Yeah.
So if we use I guess we can't use other libraries, is that true?
You can't use other libraries. Yeah, you got to stick with whatever library constraints are there. Yeah. Right. Like, well, what is there? Is there some specific library that you want?
Yeah.
Oh, Princeton's disjoint sets library. Oh, like weighted quick union type stuff.
Like
Oh, that's fine. Yeah, if you want to copy some data structure, we've already done basically. That's reasonable. Yeah. But yeah, exactly. Cool. Okay. So let's talk about Radix sorts today. That's gonna be our new topic of the day. Yeah. All right. So we're gonna talk about 2 totally new ideas. One is digit by digit sorting. And that's going to be a procedure that uses a sort as a subroutine. So one of the routines that we'll call will be, for example, merge sort. Okay. Now the word here sorts are maybe kind of a misnomer because it's not really a sort on its own. It's like a meta sort, but that's just the name I came up with. So that's going to be one of the things we do today. And the other one's going to be counting sort. And counting sort is going to be an idea like merge sort or quick sort or whatever directly competes. It is a sorting algorithm, but it's going to have a trick or difference that it does not use compare to at all. So we'll get there. Okay. Those are the 2 ideas we're going to have today. I refactored this lecture a little bit from in the past. I think it'll work better this way. Maybe not. So I'm experimenting today, but we're going to do digit by digit sorting first. So I'm going to think of it as a warm up to the big idea later in lecture. So let's say we have a list of integers we want to sort. And I just made these slides an hour and a half ago. So I hope there are not any bugs, but if there are, we'll fix them. And let's suppose that we first sort by only using the rightmost digit. Okay. So the idea here is that you'll notice that the 1s are here, the 2s are here, and then some other numbers will be down there. The idea is we're sorting by the 1s digit. We're totally ignoring the upper digit. Now you might say, why on earth are we doing this? Well, it's because we're doing it. It's a thought experiment. Okay. So question for you, assuming there's no bugs in my slide, you catch some, hopefully not. What are the 4 integers at the end of the array going to be? So just think about that. If I'm only sorting by the 1s digit, what do you get down there? Some green numbers and some yellow numbers. Okay, so I've grayed out the ones that are already there. So you only have to pay attention to those 4. Okay, what I came up with was 5, 3, 2, 3, 3, 4, 3, 4. Okay. The idea is that the numbers that end in 3 go here, and the numbers that end in 4 go there. All right, I put 53 and 23 in that order, but would they always be in that order? This is a wide open question, so you think about that for a minute. Okay, what do you think? Would they always be in this order? No, why? How could it not be in this order? Say again? Not quite. Try it. Sorry. What? Yeah, I mean, more generally. Yeah. Yeah. Yeah, if you use an algorithm that is not stable, there's no guarantee it's going to end up like this. So for example, imagine we used quicksort with shuffle. So if I do quicksort with shuffle, where we're ignoring the top digit, it may be that 53 and 23 get shuffled past each other, right? If the sort I use is stable, it'll be fine. It'll be in this exact order, but otherwise it won't be. Okay. All right. So that's sorting by the 1s digit. With a stable sort, you will get exactly this input. Use an unstable sort, you don't know which order these 2 will be in. Any questions about that? This is kind of a stability review, but also it'll be useful to us. what if we wanted stable quick sort? You can make a stable quick sort. We did. If you do the 3-pass quick sort with no shuffling, that'll be stable. Yeah. And if you're worried about the n squared worst case, you can find the exact median. If you do that, it'll be slow, but it'll be correct. And yeah. Okay. All right. So let's suppose we now sort by the left digit, the tens digit, using a stable sort. In what order will 31, 32, 34, and 34 appear? So I did the 1s and the 2s and the 4s. Those are already done. You got to figure out what goes here. Okay, what do you think? 31, 32, 33, 34. 31, 32, 34, 34. Because we're using a if I'm using a stable sort, because I'm using a stable sort, these will not cross. This is our discussion section before. We got Boss and Joni and whoever else. They're not going to get swapped past each other, right? Same deal here. We already sorted by the 1s digit. So if we now sort by the 10s digit, they will be in the correct order relative to each other. Okay. So this is a digit by digit sort. Now I'll note that this procedure doesn't work if the sort subroutine is unstable. Suppose I use heap sort or something. These could end up going past each other. Okay, so as long as that second step uses a stable sort, we're in good shape. Okay. All right. And you could generalize this to 3-digit or n-digit numbers or k-digit numbers or whatever. I don't want you to look at this too much right now, but if you want to later. This approach, this algorithm does actually work as a sorting algorithm, or a meta sort, I guess we'll call it. Where if I sort by the 1s digit, then the 10s digit, then the 100s digit, I will end up with the correct numbers. And what I'm showing here with these arrows is these are the 2 numbers that end in 3. And look, they stay in the same relative order, and they get put together towards the end. These are the numbers whose middle digit is 3. And again, they stay in the same relative order, because when you sort by the middle digit, if you're using a stable sort, they're going to stay in the same relative order. And then lastly, the top digit is 3. Well, there's 5 such numbers. They stay in the same relative order. And so we end up with the sort that works. Okay. So this algorithm is guaranteed to be correct. And hopefully this slide helps convince you of that fact. Okay. So this is a digit by digit sort. But there's a more important question, which is why would I ever do this? So there's 2 notes I'm going to make. One, this algorithm is not any better than just sorting. In fact, it's worse than just sorting by the number, right? Quick sort or merge sort or whatever, we could just compare entire numbers at once. And as you when you take 61C, or if you've already taken it, you know that you can do that comparison very quickly. You can compare an entire 32-bit number or 64-bit number instantly, basically, in 1 clock cycle, more or less. And so as a result, this procedure is just a worse version of what we did before. It's like extra unnecessary work, but we will see that this will be useful to us in another context later today. Okay? There's another note I wanted to make is that I went from least significant digit, the 1s digit, up to the 100s digit. There are other ways to think about sorting digit by digit, and we'll talk about another one of those in a bit. Okay, so any questions about this idea of digit by digit sorting, or you can call it meta sorting, because I use the sorting as a subroutine. Okay, so file this away. It'll sit in the back of your brain in this nice Technicolor color, unless you're red-green colorblind, in which case it's still got some color, but not as much as for me. And if you're a tetrachromat, you get extra colors, maybe. I don't know. Probably not on this projector. All right. I'll tell you a quick story. Ren Eng, he's a professor in our department who works on computer vision and vision in eyeballs. And they were doing a cool experiment where they were mapping out which, I forget which one's which. Rods is colors or cones? Cones is the color one? Rods is the color one? Okay. Cones? Okay, guys, no. So you got more or less, most people have 3-ish different cones. And the idea is that your cones have overlapping spectra. So there's no way that, I forget, maybe it's like the green and the blue. There's no way to stimulate just one and not the other. I don't remember exactly. But if you use a laser and you map out which one's which, you could, in theory, stimulate only literally those cones by themselves. And then you would see a color you can never see. Because it's like, there's no way to stimulate just that cone. So my goal in life is to get those lasers shot into my cones so I could see the forbidden color, where you only get one cone at a time. Yeah. The other thing, by the way, is if you take red-green colorblind primates of some kind and you inject their eyeballs with some kind of, gene editing technique, you can actually gain functional trichromacy, which is cool. So there is a way to like modify your genes to get extra color receptors in your eye. And as someone who's like interested in the philosophy of mind around color perception, I'll also volunteer for that one. So when you want to inject gene edits to get a 4th color receptor or blast my cones with the special laser, let me know. I want to be a mantis shrimp. That's my plan. All right. Anyway, counting sorts. Okay. So color perception aside, let's talk about another kind of wild idea, which is we want to get around the constraints that we have in our puppy cat dog lecture. We don't want to deal with the n log n bounds. We're going to try and get around. Okay. So we found that sorting requires, if we're using comparisons, at least n log n compares in the worst case, which means this ultimate comparison-based sorting algorithm that you could imagine the best one possible. It has a worst case runtime of n log n. So it needs to do that many compares. So that means is no matter how clever you are, you can't find a better sort if you're using compares. But if you don't use compares, maybe you could do better. Okay. Now you might say, how could I possibly sort without doing any comparisons? There's actually a few different ways to do this. I'll give you the first one, which is very goofy, which is sleep sort. Now this one requires a model of computation that does not exist, but I'll tell you what it is. So the basic idea is I have an array of integers like the ones we had earlier. And we're going to start a new, for every integer, we're going to start a new program that sleeps for x seconds. It's just going to wait x seconds. And then it's going to print out x. Okay. And we're going to start them all at the same time. And if we do that, the runtime is going to be, well, n to start up the n processes plus max a, where a is the largest integer. And you'll notice this is not n log n, right? And actually, as far as I know, I mean, I still haven't been able to track this down, but the earliest place I know of this happening was on 4chan right here, where someone wrote this algorithm that does sleep sort. So the basic idea is that you're putting the answer in the future where you'll be able to, just letting time pass. It'll be waiting there right for you. You're exploiting sort of this ability to throw the answer to a specific location and time and then wait for it to appear. So that's kind of the way I think about it. Now, this is kind of a, notwithstanding what does it mean that the runtime relates to the value itself? I mean, that's a thing that happens in computer science theory, especially in graph algorithms. But other than just that, like how does the computer actually keep track of all these sleeping processes? Well, I want to note that on real machines, there is some code that needs to keep a list of running programs sorted by sleep time in some way. So that, kind of also throws another wrench in this. So this isn't quite exactly a real thing. But if you had an ideal computer that could sleep processes like this, then hey, maybe it would be fun. Yeah. This is Bash. This is just a pure Bash script. Yeah. And Bash is a shell. Yeah. It's a thing you can learn about. That's a cute approach. So what we're going to do is something kind of like this, but instead of exploiting time, we're going to exploit space. Okay? So what we're going to do is I have here 11 records. Here are 11 different people. Here are their names. Here are their ice creams. And here is some arbitrary music that I don't know why I have. And some of them are made up, but some of them are real. Anyway, so what I'm going to do is I'm going to assume that all my data are unique integer keys from 0 to 11. Actually, there's 12 of them, sorry. And the idea is we're going to create a new array. And we're just going to copy the item with the key integer I into the I entry of the new array. Okay, that'll make more sense than to just show it. Here's the target array. We'll say, okay, so the entry that has a 5, we'll put in entry 5. Okay. Next comes Lauren. Where does Lauren go? Top, right? It's going to go to 0. Okay. What are we going to copy next? What do you think? Lisa into position 11, right? Okay, so that's a way of sorting. Now, it's a very limited special purpose sort where the keys are literally the integers from 0 to n-1, but it will work. Okay. And because arrays are very fast at putting things in arbitrary locations, it will be a very fast sort, right? We don't have to actually do any n log n. We did no comparisons. We just put everything in the place it was supposed to go. Okay. All right. So basically, avoiding yes or no questions let us dodge the puppy cat dog bound. We just sorted n items and theta n worst case time, and it only works if the keys are between 0 and n-1. Okay, any questions about this approach? I guess I'll go there. Okay, so we're cheating in a way by using space. Now, this idea actually does do something, and it will actually yield a sort that is quite fast, that does generalize. But for now, it's just a thought experiment, but we can make it work. Okay. All right. So there's some more complicated situations we need to think about. Like, what if there are non-unique keys, like there's 5 5s or whatever? What if we have non-consecutive keys, like 0, 300, 1,000, 1,000,000, right? And another one is, well, what if the keys aren't even numbers? Like we want to sort strings or something. Okay. So we'll deal with those. So I'm going to start by talking about a non-integer alphabet. Those of you who are mathy will see right through this, but those of you who are less mathy, we'll have to get there. Let's suppose we want to sort a bunch of folks, not by integer keys, but by card suits, and they're not necessarily unique. And what we're going to do is we're going to say that clubs are the lowest, then spades, then hearts, then diamonds. So diamonds will be the biggest. And so what I want you to think about for now is what will be the index of the first heart. So hearts are the second biggest thing. And I'll give you guys a minute and a half to think about this. Okay, so figure out what that first heart's going to be. And there's a yellow key. Well, maybe only a minute. Ha, I wish. Not. I'll give you a hint. This algorithm is called counting sort that we're working towards.
Oh, and these, oh, this is zero index.
Okay, question for you. How many suits are less than hearts? There's two different suits. They're the black suits. So what we could do is count the black suits. We can see that there's 1, 2, 3, 4, 5 of them, which means the first 5 spots, 0 through 4, will be occupied by black suits. And so we know that the first heart will be in position 5. Okay? So that's the idea. Any questions about that? This is the most important idea probably of the lecture, other than the digit by digit thing. Maybe that's also pretty. Okay, great. All right, so what I'm going to show you now is how I can use this as an actual sort. Like this same idea is very natural to generalize into something you could write code for. And so I will show you here a demo. Okay. So in this demo, we are going to go through and carry out the entire sorting procedure, not just putting that first heart, but all the elements in their appropriate places. So the first thing I'm going to do is count all the suits. I count 3 spades, 2 clubs, 4 hearts, 3 diamonds. Okay, that's the first thing. Now, as you know, where does the first heart go? 5. Okay, how do I know that 5 from this list of counts? It's the sum of the 3 and the 2. So what we really care about is once we have this counts array, we want to do what I'll call the cumulative sum of the array so far. 5 is the sum of 3 and 2. 9 is the sum of 3 and 2 and 4. So these 3 numbers here go into this 9. Why is this one 0? That's the first thing. Like that's the smallest suit. So we're going to start at 0. And so we'll think of these as the starting points. So the first club is in 0. The first spades in 3, hearts in 5, 9, diamonds in 9. Okay. So that's a really nice thing to know. And from there, it's actually a pretty natural algorithm, which is I'm going to have a sorted array. And I'm going to use these starting points to do my job. Now, there's 2 ways to go about the algorithm. One is to try and find all the spades and fill those in first. The other is to copy the items over here first. Okay. What's your gut feeling? Like, do you think I should copy Lauren, then Delbert, then Glazer? Or do you think I should copy Edith, then Lee, then Behrman? It's like a gut feeling. I heard some murmuring. Actually, I don't really care what your opinion is because it's already on the slide. But I want you to have an opinion, and I'm going to tell you which one I'm going to do, which is Lauren, Delbert, Glazer. Okay. The reason I like that one better is then I don't need to look for anything in this array. If I was trying to copy all the spades first, or the clubs first, I would have to actually like scan through this array multiple times. You could make it work, but it'd be a little messier. So what I'm going to do is Lauren. Where does Lauren go? I heard a 3 and I heard a 0. Small symbol, so I understand. It's actually 3. But if you couldn't see it because that's a tiny symbol, oh, we forgot to do the room control. So we're going to go to the right colors. Here we go. Okay. You guys didn't know when the class was going to start. All right, that's why we had a hard time getting going. All right. Anyway. Okay, so that's 4. Why did I change this to 4? I've populated it. I like that way of putting it. Great. So that's 4 now. Okay. So next up, where does Delbert go? 5. Good. And we increment that to 6. Okay. Glazer goes to 9. All right. Edith goes to 0 and so forth. Okay. Any questions about this procedure? Okay, so I'm just gonna work my way through it. So we keep copying. I'm gonna notice something here, which is after I copy JS, JS is a second spade, and now the starting point for spades is 5. And maybe you would call this not just starting points, but like next or something like that, next target or something. This is a 5, but there's already something in 5. So why is this okay? Because there's no more clubs, right? And we know that's safe because of the way we form this array. There was this cumulative sum here. There's no way there's going to be more than 2 clubs. So the fact that we've now added 2 is okay. So we keep going until eventually we are done. And we've sorted our array by our card suits. And how long did it take? In time. Yeah. What? We didn't compare. That's the secret. So we exploited space to save the runtime. We didn't have to look for anything. We just counted where everything was going to be up front. These are also known, by the way, as distribution sorts, this technique. And sleep sort is a form of distribution sort that uses time to distribute the items instead of space, like this one. Okay. Other questions? These sorts are actually quite old, by the way, older than all the other sorts you know. This idea goes back pre-computers. Like early census tabulations use this trick. All right. Okay. So what that did for us, it gave us an n time sort. So now let's talk about its runtime and be a little more careful. So I just made a new algorithm that is really cool, that is better than quicksort, merge sort, all the rest, because it doesn't use n log n time, but n time. All right. Well, let's be really careful about this. And I have a question. Let's suppose I want to sort the world's 100 largest cities by population. So I'm going to have Tokyo and Beijing and New York City and so forth. And I want to sort them. What do you think will be faster? Quicksort or counting sort? And this is a weird question because you have to think about what I mean by counting. So yeah, the question is, what is the alphabet for counting sort? Like before, the alphabet was diamonds, hearts, clubs, and spades. What is the alphabet now? And maybe that's the really interesting question. So give it a shot and I'll come back to you. My mental model is the alphabet is quite large. Okay, so I think as described in our demo, first question, I guess, is what is the alphabet size going to be? To me, it's the integers from 0 to whatever the largest city is. There's probably just going to be one city of each type. So I'll show you my picture here. Here's Atlanta. Its metro population from the data set I pulled this from was 6555956 and so forth. Bangalore and so is 12.5 million and so forth. And so when I do my counting array, what I'm going to do is have a bunch of cities or a bunch of populations for which there's exactly one city, and then a bunch of populations for which there are 0 cities. Okay? So in this case, quicksort will be faster because counting sort has to create an array of size 37.8 million, which, I mean, you could do it on a computer. Not so bad, but it's just a lot of work to create this big old array, add a bunch of ones, and then fill in the answer somewhere else. Okay? It's going to be pretty slow. Okay. Anybody have a different thought? No? Yeah.
Do you know the number of figures within each population?
Oh, the number of figures.
Like population 1,000, that would be 4 figures.
Oh, you could do it by like 6 digits. Yeah, you could do that, but you wouldn't necessarily get the right answer. But you could do it by number of digits, sure, right? Yeah. You get a close answer, and that'd be pretty fast. An approximation algorithm, if you will. All right. Okay. Okay, so this approach, counting sort, even though it's in time, is slower than quicksort. So let's think about this a little more. What do you think is the runtime in big theta notation for counting sort if you have n keys and an alphabet of size r? Okay, I'll let you think about this one for a minute. That's some function of n and r. Theta of n times r squared, and plus r. Okay, what do you think? Anybody want to throw out an answer? Yeah. N plus R, give me your argument. Yeah, you're gonna make an array for the entire alphabet, which is R. Yeah. Yeah, you go over the first list to do all the counts, and then you go through the whole first list again to copy everything over. So I agree. N plus R is the right answer. I think about it this way: we create and fill these count related arrays, the counts, then the cumulative sums. So if we had 4 card suits, R was full. And then we're gonna count each item, and then also later we have to copy into a new array. So it's, yeah. I have a hidden slide after this if you want to count literally every single step, but this is the basic idea. In terms of memory usage, it's going to use n plus r memory. It's going to use n to create the copy to array, like the destination array. And you're also going to use 2r for those 2 counts and cumulative sums. You could do it in one array, by the way, but I did it as 2. It's easier to think about. As the bottom line, though, is that if n is bigger than r, then we'll expect reasonable performance. But in our case, where we had n equal to 100 and r was 40 million, it's not so good. Okay? I'd like to remind you, by the way, you can think of theta n plus r as theta of max n comma r. It's the other way of thinking. Yeah. And so if r is some really big number, we can be kind of. All right. Yeah. Is there any runtime cost too? There is the cost per indexing. Like I have Lauren, she's a heart or whatever suit she was. Going in and finding where she was is very fast because we're going to assume that we could do that in constant time because the alphabet is like a small integer alphabet. You would use an array, basically. Yeah. There might be some indirect cost. Like let's imagine that that's stored as a map or something, then it would take log r time for lookup. So it kind of depends on the detail, but log r versus constant's pretty small. Yeah, good question. Right. Okay. Now, if you want to know what's actually faster in a particular circumstance, you would actually need to do some kind of empirical experiment. And we're going to do a little bit of that in our sorting summary lecture in a bit. Not today. Okay. All right, one more question for you since I keep throwing these out at you. There's supposed to be an A and a B here. Sorry, this is supposed to just be bullets, but I don't want to spoil it. So imagine those just bullets. There's not 2 choices. So I want you to give me an example of a specific situation where counting sort is going to be a lot faster than quick sort. Okay. Just a small one. I'm not going to be long on this. So I gave you an example where quick sort would be faster. What's one where counting sort would be faster? Big N, small r. So what's an example of that? Yeah. Oh, 100 cities by continent. Oh, that's interesting. Right. So like one continent is 1, 2, 3, 4, 5. Sure. Yeah. What do you think about that? I think that's fair. It's so small. I don't know. That's a little stranger one. I'll give you one I had in mind, which was imagine you have I don't know, numbers between 1 and 1,000, and you have a billion of them or something. Then you'll clearly blow it out of the water. Okay. Anyway, all right. So counting sort is a cool idea. Let me compare it to our other sorts. Quick sort, we had n log n expected runtime. It was the fastest comparison-based sort. Counting sort had a runtime that was n plus r, where r is some alphabet. And usually it's kind of weird to say that r is a variable, but in real world situations, we can actually end up in a situation where r is quite large, like counting a bunch of cities. Okay? So counting sort, I'd say, is nice, but the issue we have is twofold. One, it's not going to be super efficient if r is really big. And two, there are some things that just really aren't really countable in the same way. I mean, they can be. You can finesse it into being. But like, imagine trying to sort strings using a counting sort. Kind of weird to say, like, okay, we're going to count all the words that are A, then all the words that are B, and then all the words that are AA and AB and AC and so forth. And so what we're going to do is combine our two ideas from today, and it's going to fix all of our problems. It's going to result in a counting sort variant where r is small and which generalizes to things which are not from a finite alphabet, like, say, strings. All right. So what I'm going to do now is present a version of like a combined idea of these two that's going to give us our first radix sort. Okay. So counting sort, as we saw, slow when the alphabet's really big. But if we decompose our input, and that's the very clever idea, into a string of characters from a finite alphabet, we can basically force r to be now a small thing. Okay. So for example, imagine we're sorting numbers. The problem we had with the population of Tokyo is it was 37 million. But if you think of 37 million as a sequence of digits, then we'll be in better shape. In fact, what will be our alphabet size if we decompose it into a sequence of digits? 10, right? If you break it into a sequence of single digits, you could actually break it into pairs of digits, and then it'd be an alphabet size 100 or whatever else. But I'm going to stick with the most obvious choice for now and say we're just going to go by single Arabic numerals. That's what we're going to do. Or equivalently, we could do single card suits. So if we had 2 card suits per person, they're playing, I don't know, Texas Hold'em or something. Or if I want to sort by strings, like horse. Here we decompose into a sequence of digits, and now the alphabet is of size 26. Alphabet size here is 4. Alphabet size here is 10. Okay. That's going to be our clever idea. So as you know, when we do digit by digit sort, that was the beginning of the lecture, we first sort by the right digit, the smallest digit. Before it was the ones digit of some numbers. Now it is the first or the lower card suit. Then when I sort by the top card suit, because it's stable, whatever sort we're using, we'll be in good shape. Now, what I'm going to do is the new thing is instead of using any arbitrary sort, we're going to use counting sort. Okay. So we could have used like insertion sort or something else, but here I'm using counting sort. And the reason, what's the advantage of using counting sort over merge sort here? Let's say. Merge sort's also stable. Good thought. It's another reason. It's faster. What's its runtime? N or N plus R, but R is a small thing. It's like 10. Whereas merge sort costs what? N log N. So we're going to use counting sort because it's faster. Okay? Now you can do a digit by digit sort with any sort, but if you pair it with a counting sort specifically, you'll get something that works. It'll be very fast. It'll be so fast and important that it has a special name. Okay? Now you could do that whether it's card suits or whether it's numbers. These are just the exact same thing, right? And for the mathy folks, I mean, for you, yes, these are just integers, 0, 1, 2, and 3, or 1, 2, 3, and 4. And so it's the same, right? Okay. Now, this approach where you combine a digit by digit sort with a counting sort, as I said, it's such a special combination that it's got a special name called a radix sort. Okay. Now, radix is a term. I just took the Wikipedia definition. So if you have a positional numeral system, like say Arabic numerals, the radix is the number of unique digits. So with numbers, it's 10. The radix here is 4. That's a radix. Okay. And so the sort we just described, which is digit by digit from the least significant digit to the most significant digit using counting sort, that is known as the LSD, or least significant digit radix sort. Okay. Right. I had to this morning go back to Donald Knuth's book to see exactly which thing is a radix sort. It's this whole combination. According to Knuth, so I'll just trust it. Okay. All right. So question for you. You should be convinced this sort works because it's just the combination of the two ideas we had before that we feel like they work. So I'm just going to skip correctness and go straight to runtime. What do you think is the runtime of LSD sort? And so it obviously has an in term, but I want you to make up an additional letter for something else that you might think of as non-constant. So let's say R is I don't know. Well, I don't know, whatever. I don't remember what I did actually. I'm gonna look at my hood. Okay, what did I say? Okay, I want you to have N. Let's count the alphabet as its own symbol. So there'll be R as well. And then pick a new letter for one more interesting quantity. So you got to identify, first of all, what's the interesting extra quantity? Give it a letter, and then tell me the runtime. I'm gonna give you 2 minutes on this one. Talk to your neighbor. This is a hard question. Reminder that counting sort is N plus R. So I want you to come up with some new formula for LSD Radix sort. It's going to be slightly different. All right, I'm hearing answers I like. So we're gonna do how many counting? So we're gonna do some passes of counting sort here, right? There's gonna be N plus R, and we're gonna do some number of passes of counting sort. How many? The number of digits. Okay, so I picked, what letter do you want for number of digits? L. L's pretty good. I picked W, but L's fine too. So I picked W, and so it's just going to be W passes of counting sort. So the overall runtime will be N plus R times W, and I just distributed that. Okay. That's a pretty hard question to just throw at you. A little vague, but hopefully you found the exercise useful. All right. So the overall runtime of LSD sort is WN plus WR because it's just W counting sorts. Okay. All right. We'll come back to comparing it with merge sort in a second. Yeah, any questions about this? All right. So after we finish our least significant digit, we can occasionally run into trouble because it is the case that maybe W, I mean, I was picking numbers that are all 2 digits, but what if I have a mix? What if I have some like 9s and 51 and 817 and so forth? So one thing you could do if you have some numbers that don't have, leading digits, or say you're doing strings, like you have potato and cat. So how do you sort those? Well, you're going to treat the top 3 digits. You can just treat them as empty spaces that are less than all the other characters. Okay. Got to be careful with that. Right. With the words, it's a little tricky. With numbers, you pad appropriately. You'll be in good shape. Okay. So if I do that with numbers, and I'll leave it as an exercise for you to think about words. If you think about numbers, though, here it'll work perfectly fine. So I'm going to treat this dot as a character that is less than all other characters. And so whenever I sort by this top digit, we're going to end up with blank, blank, 9. Okay. And the reason it's different between words and numbers is because if you don't have a number at the front, you could think of it as a leading 0. Okay. And so this will work just fine. Okay. All right. So what we end up doing, as I said, was W passes of counting sort. But we have this annoying feature that the runtime depends on the length of the longest key, which isn't ideal. Okay. So I'm going to call back some old friends, and I'm going to have now an asterisk next to them. This asterisk is new on this slide. And did you have a question? No, okay. This asterisk here is new on this slide because now if I'm trying to compare merge sort to LSD sort, it's a little dishonest that in LSD sort, I'm counting the width of the longest key. Whereas with merge sort, no, I just I call it n log n. But of course, if you're comparing 2 strings, does the runtime for comparing 2 strings depend on the length of those strings? I heard a yes and a no. Sometimes, that's a great answer. When would it matter?
They like have the same characters, but like different, like start versus starting.
Right, so there's some strings where it doesn't matter, the length, like start versus starting. Takes a little more time to compare because you got to go ways in. So for strings that are relatively similar to each other, then the compare time does depend on the width of the string. And so that actually kind of leads us into our last algorithm of the day, which will be MSD sort. Okay. But I was just adding this asterisk because I want to be clear that I'm cheating a little here. And I'll come back to this row in the sorting summary lecture. Okay. So we got one more sort for the day, which is MSD radix sort. And so going to what you were saying, the idea is that when we're comparing two strings, LSD sort is going to be doing something worse than merge sort. So if I tried to merge sort these 5 words, I don't have to really look at the rightmost characters at all. Whereas what LSD sort will do is it'll start and look at the rightmost characters of my words and work their way to the front, basically doing all this useless work, looking at the trailing digits until you get to the leading digits. Okay, so that's not so ideal. Okay. So I'm going to suggest that one thing we could do is think about the top digit first, because if I have anti-disestablishmentarianism, which probably is some word that you learned at some point, maybe, or heard of, then as soon as we see this A and compare it against the others, we're just done. So question for you. This is my last question of the day. Let's suppose we do topmost digit, then middle digit, then rightmost digit. So we're just doing digit by digit sort from the beginning of the lecture, but flipping it around. Will this work? Okay, I'll let me think about this for a minute. Okay, I'm gonna tell you that in fact it does not work. Okay, here's why it doesn't work. Consider this case. So if I sort by the top digit, I get add, ace, bad, b, bad, cab, and so forth. When I sort now by the middle digit, we have a problem. Bad gets put up at the top because it has an A in the middle, whereas add gets put down here somewhere because it has D. Okay, and that's not going to get fixed when we sort by the last digit, right? Because they're both D. So we made a problem. So next question is, how do we fix this? So let me think about that one for a minute. I lied about that being my last question. Go.
We get the less really want it. This you got like quick decision and be like, oh, this is like the A zone. Well, then that's just the other. Things sort by the second. Sort from right to left. Like that's what it is. Like that's
Okay. All right, I'm gonna take a suggestion. What do you think? How do I fix it? There is a pretty natural fix. I heard it said. Go for it.
make it so that none of the A's can go below like two, like you partition all the letters.
Partition them, yeah, like set a line, like a wall. That's exactly right. So what we're gonna do is say these never need to move. We treat it kind of like in quicksort. When you partition, you land in the middle, you have two separate subproblems. How many separate subproblems will I end up with here? Yeah, 4. One that's trivial, but 4 problems. So what we're gonna do is basically split it into 4 worlds: the A world, the B world, the C world, the F world. And there's a pretty natural recursive algorithm that comes out of this. Kind of interesting with the LSD approach, that doesn't happen, right? But with the MSD approach, it absolutely does. So now what we'll do is we have 3 separate problems. Now we can sort these with any subroutine we want. In this case, what should we use? What do you think? It's kind of a mean question. So we could just recursively do this process, but if you had to pick a sort to resolve these 3, what would you do? Insertion, right? So technically, actually, how this algorithm is usually done, you have a whole lot of strings, you break them into a bunch of subproblems, and if any of them is less than, say, 15 or 20 or 30, you just insertion sort that little chunk. Okay, but we're not going to do that. We're going to keep doing MSD sort. So in this case, we're going to get 2 subproblems with this, the AC problem and the AD problem. Okay, what are we going to get here? How many subproblems? The BA and the BE problem. Okay, and then we're going to end up finishing up like so. And this is how, if you really were to go to that like nth degree or that Wth degree, I guess, that's how you could do MSD radix. Okay, that's kind of fun that LSD radix sort doesn't have this kind of fractal recursion thing going on, but MSD radix sort does. Okay. And this algorithm is a real algorithm, and in some cases, it's pretty fast. Okay. You have the stamina. Actually, any questions? Yeah. Could you turn MSD into an LSD sort by flipping the keys? I'm not sure what that would mean exactly. I'll think about it while you guys think about this if you want. I forgot I had this question in there. You're probably kind of tired, but let's try anyway. Good luck. How about this? If you don't want to find the formula, give an example of a best case input and an example of a worst case input for MSD sort. Okay, I'm ready. So what would be a best case input where MSD radix sorts super fast? Yeah. Every element's its own partition. Yeah, all the top digits are different. And what would be an example of a really bad case for MSD sort? What's that? Only the last digit differs, right? Something like that. So in the worst case, we have to look at every single character. And in that case, it basically degenerates into a very similar thing to LSD sort. It's equivalent because it'll look at every single character. Whereas the best case, if we finish in one counting sort pass, we only actually ever look at the top character. Now, there's one really, really, really subtle error in this argument. Anybody spot it? This is mostly true. It's not quite true. So as n gets really, really big, why is this a problem? Yeah? Well, not quite. There's like this thing I'm saying isn't even possible when n gets really big. Yeah? Right. If n gets bigger than r, you just can't have that anymore. So imagine you have an alphabet of size 10 and a million items. They can't differ in that top digit. So you have to be a little more subtle than that. But this is roughly true as the best case. Okay. So I'm wrapping up here saying here's all of our sorting algorithms. We're going to come back to this table and talk about it a little more. And the last thing I wanted to suggest is, I'm not going to do it right now, but now that we've seen LSD sort and MSD sort, you might find it fun to try and answer these questions about LSD sort. Okay, thanks everybody, and I'll see you guys on Wednesday. Hi.
I missed the last thing that you said, about why it was like coded with Trinity.
Once again.
I missed why you said that explanation was just flawed.
Oh, because let's imagine your alphabet